see everybody ready to go. They're all back in the seat already. We have to run everybody back in. So we'll go ahead and get started in section 2 of our manual. This section deals with asphalt materials. Basically, we're going to be talking about the asphalt binders and the aggregates that are used in our asphalt paving. Before we get into that, the third paragraph down on page 2-1 tells you that in 1987, the Strategic Highway Research Program, or SHARP, started developing a new program for designing, testing equipment, and stuff like that. The final outcome of that is called BasicPavt, which is an acronym for Superior Performing Asphalt Paving. Don't let that mislead you. Just because it's superior performing asphalt paving, don't mean once you pave something with super pave, it's going to last forever. It's just not going to do it. We have some of the same problems today with super pave mixes as we did with our Marshall mix. But just to point that out to you. It'll go on in that paragraph, tell you that it specifies binder requirements, aggregate requirements, testing equipment, and just other things there. It was all based off of environmental conditions and traffic loading. So with that, we'll start getting into our asphalt pavements. Down at the bottom of the page, you see several different types of asphalt pavements that are listed. The first one listed there are our asphalt concrete dense graded mixes. These are probably the ones that we're most familiar with and the ones we do use the most. These are our base, intermediate, and surface mixes. They're called dense graded mixes. Then it goes on to mention friction courses, bonded wearing courses, surface treatments, emulsified mixes, permeable mixes, and then your other things such as SMAs, and then your in-place recycle mixes such as hot in place and cold in place recycle mixes. I don't know, but about 2 projects that we've done of the cold in place. One of them was right here in Winston-Salem on 158. But we do, or now starting to use a lot of hot in place recycle. We've got a couple of projects underway right now. This is a process where the contractor has a long paving train. We've got a series of heater banks, goes along, heats the pavement. Then there's a milling machine that mills it up, puts it in a windrow, picks it up, runs it through a plug mill where there's rejuvenating agent added to it. Then if it's required, we do add some type of what we refer to as admixture. And it's basically just another dense graded asphalt mixture. Sometimes it will have 5 or 6% binder in it. Sometimes it won't have a 1 or 2% binder in it, depending on the type of mix that you're trying to turn it into and what the binder content needs to be to get your proper volumetric product. And then it's placed right back. It never leaves the road. It stays right there, paper right there. They put it right back down, roll it, test it for density, and that's basically how that operation works. Any questions? Going on over to page 2-3, the first big heading there talks about the classification and grading of asphalt pavement, and it lists 3 things. It's got, let's see, your asphalt binders, your cutback asphalt, and your emulsified asphalt. Before we get into that, I'll just point out to you that the state of North Carolina does not allow the use of cutback asphalt. They are cut back with some type of petroleum product, such as naphtha, kerosene, stuff like that. And due to environmental concerns, with that stuff evaporating out of it and getting into the atmosphere, we do not allow the use of cut-back asphalt. Basically, we're going to be talking about asphalt binders. That's the binder, the asphalt that we put in with our aggregates to make our dense-graded mixes. As I mentioned, there's specification requirements for your asphalt binders based off of your environment and traffic labeling. Down in the last paragraph, it refers to PG 64-22. This is the most common grade that is used in North Carolina based off of the environmental conditions in most traffic labeling. But it tells you there that PG stands for performance graded. The 64 is in degrees Celsius, which is approximately 148 degrees Fahrenheit, which means that asphalt binder should perform as its expected temperatures up to 148 degrees. The minus 22 degrees Celsius is equal to approximately minus 8 degrees Fahrenheit, which means it should also perform as low as minus 8 degrees Fahrenheit. And these are referred to as the high grade and low grade temperatures for that mix, for that binder. And we'll look at a chart here in a little bit that gives you a little better perspective on how it works. Over on the next page, you see a little flow chart. Asphalt binder is a constituent of petroleum. When an oil well is drilled, when the crude oil comes up through the well, it'll go through field storage, pumping stations, and go down through the heating tube into a distillation tower. In that distillation process, the first thing that comes off in that distillation process is our $4 a gallon gasoline. The next thing would be your kerosene or light burning oil, and then our diesel oils and light and lubricating oils. And then down at the bottom of your distillation tower, the residue that is left is our asphalt binder. As you can see here, they call it asphalt cement. This is an older overhead, but it's asphalt binder or asphalt cement comes off. And if you follow the process on down, in that process they have stations in which they make you cutbacks, which we do not allow the use of. It goes on down to emulsified asphalt. This emulsified asphalt goes through a special process where it is mixed with water. And you say, well, you can't mix water and asphalt. And you're right, you can't pour asphalt into this cup, pour water in it, and mix it together. You can't do it. With that emulsion plant here, a special process in which they encapsulate the asphalt binder molecules with the water, and then when it's sprayed out on the road, that water will evaporate and leave the asphalt binder in place. But that gives you an idea of how we come about getting to our asphalt binders from our crude oil. Any questions on that? The next couple of pages goes into your asphalt binders, your emulsified asphalt. Then it goes into characteristics and stuff like that. We do not have time to go into that in this class. There's other classes that you go to that you will spend a lot of time on those subjects. Over on page 2-8, you see there asphalt additives. We do add additives to our asphalt binder. two listed there is silicone. Silicone, by our specifications, is required to be added to all asphalt binder used in surface mix. And it goes on to say that it's required to be added at 1 to 2 ounces per 2,500 gallons. And you say, well, what is 2 ounces going to do to 2,500 gallons? I don't know the answer to that question. All I know is if you're having certain problems, it will work. If you're having dragging and carrying problems out on the roadway, it will help alleviate that. If you've got moisture, it will help get rid of the moisture. But it does work. The next one is anti-strip additives. This can either be a chemical or liquid type anti-strip, or it can be a hydrated lime process. We don't use a lot of lime in North Carolina. I know South Carolina uses lime quite often, but most of the anti-strip that we use here in North Carolina is a chemical or liquid additive. The reason for that is that we put that in is that some aggregates and asphalt binders just don't, that binder will not stick to that aggregate as it's supposed to. So we put that in there to help that binder adhere to the aggregate. And it is required by spec for all super paved mixes to have at least 0.25% of anti-strip additive in it. Based off of field test during the design process, it is determined on just exactly what the exact rate is. I've seen it go from anywhere from the 0.25% that's required up to as much as 1%. And that, like I say, is based off of field tests that are run at the design process and during production. Any questions on that? Then we go into the asphalt binder storage. Again, we don't cover that in this class. I mentioned earlier about looking at a chart over on page 2-11. All down. You see a listing there of your performance rated binders. Both the high grade and low grade temperature are shown. On the left side is your high temperature grade, and it ranges from a PG 46 up to a PG 82. You can see I have it bolded with an arrow there. The PG 64 minus 22 is the grade, is the most standard grade that we use on both high and low ends for our asphalt patients in North Carolina. Based off of certain environmental conditions, traffic loading, and things like that, we may have to step up to a PG 70 minus 22. And then as we get into heavier or a lot more truck traffic, that's what it's based off, is truck traffic, we may go up to a 76 minus 22. I'm not aware of using any 82 as of right now. But some of your major interstates, such as I-85 around Charlotte, and then here in Greensboro, Winston-Salem, we would require probably a 76 minus 22 due to the number of trucks that do use that facility. Any questions on that? On the next page, you'll see two charts listed. The top chart is just talking about your emulsified asphalt. We won't go into that, but I'll just point out to you the bottom chart, table 2-3, which is an emulsified binder which is used for our prime coats. These are 4 individual companies that are pre-approved to use their product in prime coat. And as of the printing of this manual, these were the only 4 that are approved. So if you happen to get on a project that calls for prime code, and when you get the bills laden in, you look at it and see if one of these manufacturers are not on that list, you would need to contact Materials and Test and check with them about whether that particular product is approved. You can go to their website, that's listed there, and pull up, I think, the most current listing for approved lists. But just keep in mind, if these, as of the printing of this manual, was the only approved sources. Going on over on the next page, about a little more than halfway down, it gets into your mineral aggregate. And as you can see there are several sources of aggregate. The first one listed there would be your natural aggregates, such as natural sands, river rock, what I refer to it as. River that is rock that has been dipped out of streams, rivers and stuff like that have been eroded by water and weather, and they are highly rounded aggregates. They're like marbles. Matter of fact, they're kind of hard to get density on the time because those aggregate particles will roll around in there. A lot of contractors that have access to these natural aggregates like that now run them through a crusher to get some fractured faces on to make sure, or to help their compaction process. The next one listed is your processed aggregate. These are quarried materials. These are aggregates that come from quarries where they have gone in and crushed it down to different size fractions, keep it stockpile at the quarry, and for the contractor to haul back to his plant site to use. There's several different sizes, and we'll look at some of those in a little bit. The next one listed there are your synthetic or artificial aggregates. It mentions one particular there is your blast furnace slag. This is the residue that is left from the smelting of iron. When you go through the process of smelting iron, the slag will float to the top, and then they will get it off. And after it cools, they can process it slightly and use it in asphalt materials. And then on the next page, it talks about recycled aggregates. We're probably more used to reclaimed asphalt pavement. This is where we go out on the road, mill up the existing pavement, take it back to the plant site, go out here, tear up a parking lot, take it back somewhere, have it crushed, processed, and then used back into our asphalt material. Any questions on that? Now, I mentioned earlier that SHARP program specified different types of tests that are required for your binders and aggregates. Listed down below our aggregates, there are certain tests that are required. We have what we refer to as source properties. And you see there is toughness, soundness, and deleterious materials. And then it goes through giving you a write-up about what test procedure is required, either AASHTO or ASTM test procedure, and what the requirements are. Due to time, we won't go through all that. You can read it just as good as I can tell you about it. The next one listed there are your consensus properties. There are 4 of those. You've got your coarse aggregate angularity, fine aggregate angularity, fine flattened elongated particles, and your clay content. And then once again, the ASTM procedure and requirements are listed down below those. Any questions? Over on page 222, you'll see a chart listed there, table 1005-1, that comes directly from our standard specification book, which is that red book Wayne showed you earlier. And if you look down the left-hand side of that, you will see different sizes of aggregates. It starts off with your large number 4 aggregate, goes down through your 78 M's and 14 M's, including your ABCs. And then across the top, it lists different size sieve designations with a gradation range on each one, and that aggregate to meet the specification requirements must fall within that range of that particular sieve. That just gives you an idea of the types of aggregates we use and what the gradation requirements are. The next page is actually just a continuation of that chart. We didn't have room to put them all on both on the same page so you could read it anyway. But this is just a continuation of that chart, and it gives you a little guidance there on what the producer's spec requirement is. And then once it's stockpiled at the yard, it has to be tested. Then it's loaded into a dump truck, taken back to the plant site, it's tested again, and it's a little bit different tolerances there on the gradation requirements due to handling and stockpiling and stuff like that. But I won't go into that now. One thing I will point out that this chart is for coarse aggregates only. It does not include fine aggregates. You would have to refer back to your spec book in section 10 to see your requirements for your sands, screenings, and stuff like that. Any questions, comments? Good thoughts, bad thoughts? Not, I will turn it back over to Jim.
You'll turn now to section 3 in the manual. This section is titled Asphalt Pavement Design, and probably most of you will never be involved in actually designing an asphalt pavement structure. Somebody may have been. Probably most likely not. Even our pavement construction section is not directly involved in the design of asphalt pavements that are used by NCDOT. There's a section within the what's called a pavement management unit that actually does this. They go out and take all kinds of surveys and gather traffic information, including the total number of vehicles, percentage of trucks, do a subgrade soil analysis in most cases, and then eventually come up with a pavement thickness or pavement structure that is going to carry that projected traffic. And there on page 20, or rather 3-1 up at the top, notice that most pavements were designed for a 20-year period, and that's not to say that at the end of that 20 years, the pavement will have to be totally rebuilt. Hopefully with adequate maintenance as you went along, you know, proper resurfacing. At the end of 20 years, you could do some maybe major rehab work and establish that pavement such that it would last for another 20 years. So, but generally, you base it on a 20-year design period, and you want to come up, you know, with a pavement thickness there that's thick enough to carry that projected traffic. One that's going to be, you know, relatively impermeable and not damaged by water and rain, you know, that accumulates, and then have a top surface that's smooth, dense, is going to be able to, you know, to perform under all kinds of adverse weather conditions, as well as, you know, various traffic loads that's going to be applied to it. And when down at the bottom there, you'll see a drawing there that shows the tire load being applied to the pavement structure. And ultimately, the subgrade is going to carry that load. But if the tire load was applied directly to the subgrade, probably you wouldn't be able to withstand very many passes before it started deteriorating. So the idea there is to put some pavement there such that the load is spread out as it transmitted down through the pavement. It will spread out to the point that the subgrade will be able to carry the load for many, many, many applications. I think if it spreads out, the stress is going to be less, so the subgrade will be able to carry it. And if you just think about it, the stresses in this pavement structure are the very greatest in the surface layers. So those layers actually have to be stronger than the lower layers, because the stresses are going to be great. And I think you can also see, you know, that the thicker that pavement is, the more it's going to spread the load, and therefore the pavement will be able to carry more load. That's the basic idea there. Some pavement, you know, depending on the traffic load, may just consist of surface layers that are placed directly on the subgrade, or aggregate base in some cases. If you have heavier traffic, you may have both an intermediate layer and surface layer. If you have real heavy traffic, you may have an asphalt base, intermediate base, asphalt course, again, with surface layers applied. And in some cases, it's maybe more economical to go in and strengthen the subgrade as opposed to adding additional asphalt thickness. It's probably more true today than ever before because of high asphalt prices. That's sometimes why we go in and we'll add select subgrade material or condition the subgrade material with lime or cement, whatever the case might be. Economics plays a very important role in pavement design. Over on the next page, it lists there at the top of the page 4 the major things, I think, actually 5. They go into pavement design. One of them, of course, is the traffic. And when you're designing a pavement, when you say traffic, it's primarily the number of trucks that are going to be using that pavement that really influences how thick the pavement needs to be. Now, obviously, the total number of vehicles that you'll have using a section of roadway determines whether you need 2 lanes, 4 lanes, 6 lanes, or whatever. But it's the trucks that really drive how thick that pavement needs to be. If you notice here, it says 1 passenger tractor trailer equals approximately 4,000 passenger vehicles from a pavement design standpoint. So it's really the trucks and types of trucks that makes it different. And some soil support value, that's related to the subgrade. Obviously, some soils have stronger strength values than others, and so on, so that comes into play. A regional factor is applied with the same exact conditions for traffic and subgrade strength and so on. Pavements in western North Carolina will be slightly thicker than pavements in central and eastern North Carolina. Why would you think that's the case? More freeze thaw cycles, more ice, snow. When it does freeze, it freezes to a greater depth. And so the problem is not when it freezes, the problem comes about when it starts thawing. And so that's taken into account. The strength of the different layers themselves, as I said earlier, the surface layers have to actually be stronger on a per inch basis and the lower layers because that's where the load stresses are the greatest. That's where the tire load is being applied, and so that's where more rutting is likely to occur, and so on. So those layers have to be very stable such that they don't rut. And we'll talk about that in a little more detail here in a few minutes. And then, of course, the economics comes into play. As I said, you want to consider that. It may be cheaper to strengthen the subgrade as opposed to asphalt thickness. In general, your coarser layers, like base and intermediate, are less expensive than surface layers. So you can consider that. The economics certainly plays a role in design of pavement. Down at the bottom of that page, you'll see that tire load being applied to the pavement again. And when the tire load is applied, there's some deflection that occurs. Hopefully this is exaggerated for illustrative purposes. But when it bends directly under the tire, the upper portion of the layer will be in compression, the lower portion in tension. And because the curvature is the opposite out on either side, the reverse is true. When a vehicle moves along the pavement, it's constantly causing deflection in that pavement. And it's sort of like the deal where you take a piece of wire or a metal bar, and you can bend it a little bit, and as long as you don't bend it very much, you can put it through many cycles before eventually maybe it'll start cracking and breaking. But if you want to really make it crack and break in a hurry, what do? You bend it a lot. And that's just, significantly reduces the number of cycles that it would go through before it starts cracking and breaking. And basically, that's the same concept with the pavement. When you're designing that pavement, you want to design it so that you minimize that deflection. And I guess you could build a pavement out where the deflection would be virtually zero. But if that was the case, it'd probably be real thick and very expensive. So again, you have to keep economics in mind. The idea is to minimize that deflection, to the extent possible, such that it can undergo many passes of vehicle tires over, before the dust starts fading. But all these things considered, we came up with the SuperPavt MixTypes. These are listed there on page 3-3 in your manual. As Bob mentioned earlier, SuperPavt was a design concept that came about a number of years ago to primarily address rutting. There was a lot of rutting that was occurring in pavements, not so much in North Carolina as in other parts of the country, but we had some of it too, but it was caused by a number of things. Winter pavement is most susceptible to rutting. It's hot. That's when the asphalt binder gets soft, and that's when the pavement is most susceptible to rutting. Now in the western part of the country, we had several years of real hot weather where it stayed just hot day after day after day, and those pavements got real hot, real deep, and just stayed that way. It didn't cool off significantly at night, and so that contributed to rutting. Along by the same time, tire manufacturers were changing, modifying the way they made tires. And we're going from a design pressure on 18-wheeler type tires from 100 psi to 140 and 50 psi. And that just focused or concentrated that load into a smaller area. And that increased the load, the stress that caused rutting, additional rutting. And then about the same time, you probably know, the trucking industry has a real strong lobbying effort in both Congress and in the legislatures. And they got these people to increase the legal load limits, and that just compounded the problem. So all these things go to a lot of rutting and pavements. So the Federal Highway Administration got involved in it, and out of all that research that we did at that time came SuperPavt. Bob mentioned just an acronym for Superior Performing Asphalt Pavements. There was some part of a common misconception that it was going to solve all the paving problems, but that's not really the basic concept. That's not necessarily true. The super pave specifications were set up to be a performance graded pavement. That's how they came up with the PT gradings on the asphalt binder. Those binders are supposed to be selected for a given pavement based on the expected performance of that pavement under a given condition. And pavements, with lower traffic can be, have not only less thickness, but you can use, I won't say inferior materials, but they don't have to be as high quality as you would want to use in pavements that have a lot of traffic. And so that was the basic concept. You would come up with a pavement and mix that would, perform based on the expected performance and conditions under which it would be exposed. Out of that again came the super paved MixTypes on phase 3-3, or the grade or mixed type designations that we use here in North Carolina. Other states use something similar, not necessarily the same designation method, but here we have, in North Carolina, we have 3 basic types of pavement, super paved mixes. It's one of those things you need to remember for this afternoon. We have surface mixes, and up here when you read the fine print up at the top of this page, we talk about surface mixes. Those are the upper layers, obviously, of the pavement structure. Down below that, we have intermediate mixes. These are somewhat coarser mixes than the surface in general, and so on. And then on the bottom, if you have all 3 layers, you would have base coarse mixes. So we have surface, intermediate, and base. And if you look at the mixed types, you'll note that it's always, they're designated with a letter followed by a number, followed by another letter. And that first letter in that mixed type designation refers to whether or not it's surface and intermediate or base mix. There is one exception here, and I'll talk about that in just a minute. But in every case, again, the number is followed by, the letter is followed by a number. That number is related to what is called the nominal maximum aggregate size in that mix, not the P maximum, technically, what's called the nominal maximum. But again, in any event, it's related, to the top size aggregate in that mix. And if you'll notice here, we've got 4.75, 9.5, 12.5 on surface mixes, 19 on intermediate, and 25 and 37.5 on a base mix. Now those numbers are in millimeters. Now why they're in millimeters, I'm not sure. The only reason I've ever come up with was because when super pave was being developed, metric was the going thing, and so they designated these aggregate sizes in millimeters. But just to give you a feel, if you're not metrically inclined, and neither am I, but 9.5 millimeters is about 3/8 of an inch. 12.5 is about 1/2 an inch. 19 is about 3/4, and 25 is about an inch. So as you see there, it just makes sense that the surface mixes have the smaller top size aggregate, intermediate, or in between, and then the base mixes have the largest coarse aggregate. And then the number is followed by a letter. That letter is related to this column right here. Related to the traffic and loading that pavement is going to be exposed to over that 20-year life. If you'll notice there we have 4 levels, an A, B, C, or D level. A is the lowest level of traffic, D is the highest level of traffic. And again, it's related to this column, what is called an ESAL range. Now you don't have to, what is ESAL, E-S-A-L stands for equivalent single axle loads. It's a way of converting these pavement management people who design pavements. It's a way that they convert the traffic information to a number that they use in their design process. So somehow or another related to 18,000-pound axles and so on. Passenger vehicles have a practically almost zero diesel rating, whereas a legally loaded tractor trailer have a high, very high diesel rate. But in any event, it's related to traffic. As I say, there's 4 levels. A is the lowest level. A level fixes are designed primarily for your low traffic, say 2-lane secondary country rural roads, whereas at B level is for higher traffic. Maybe your primary routes, lower primary routes, low traffic primary routes. The C level probably is for heavy primaries and some of the rural interstate system. And then the D level traffic is for very high traffic interstate type traffic. And there may be some primary routes that fall in that same category, but for the most part it's for interstate type traffic, where not only do you have a lot of vehicles, but you have a real high percentage of trucks. And that's what drives that incident. Now the next column here is related to the binder grade that has been selected for those various mixed types. The way these were selected in North Carolina is by using the climatic conditions. The BasicPavt guidelines say that you want to select the grade of binder that you're going to be using based on the average 7-day maximum pavement temperature that pavement is going to be exposed to. And then the second grading is based on the minimum, it doesn't say 7 days, it's the actual minimum 7-day average temperature that pavement is going to be exposed to. And there are many grades, as Bob mentioned back on that chart in page 2-11 of the manual. Obviously, we wouldn't use all those. In fact, we don't need all of them. The way you select the grade is to go out and actually do surveys based on a given location to find out what the maximum and minimum average 7-day temperatures are and so on. We did that for many locations throughout North Carolina, and it turns out that for the most part, on the high end of the scale, PG 64, and that's degrees in Celsius, which is about 147 degrees Fahrenheit, would suffice for most of North Carolina. There is an exception down in the southeastern part of the state, down around the Sand Hills, Fayetteville, Southern Pines, that area. Probably you would want to use a little higher grade. But again, for the most part, PG 64 would be the standard grade. On the lower end of the scale, when we look at North Carolina as a whole, minus 22 degrees would be the grade that we would want to use. Again, there are a few exceptions to that. Up in the higher elevations in the mountains, we do have sometimes the average temperatures that get down below that minus 22. Minus 22 is minus 8 degrees Fahrenheit, to give you some perspective. So, looking at the state as a whole, it was decided that PG 64 minus 22 would be our standard grade, based on average high and low temperature. And the BasicPavt specs say that once you've selected the grade based on environmental conditions, you want to consider the traffic loading that's going to be used in that pavement. And that you may want to use different grades, which would mean a higher temperature grade, for those conditions or situations where you have real heavy traffic, and especially a lot of truck traffic. So, using that concept in mind, and looking back at our MixTypes table, you'll see there for those lower traffic levels, and this comes into play in the surface mixes primarily, to some extent maybe in the intermediate and base mixes. So the reason you're concerned about the surface is that's where the rutting is going to be, rutting potential is going to be the greatest. So on our lower traffic mixes, like on A and B levels, we use PG 64. And because of that lower traffic, we don't adjust that based on the load. When we do get to the C and D level, where we have heavier traffic, then we want to consider that. So if you'll note here on the 9.5C and 12.5C mixes, we bump, the term they usually bump, where you increase the temperature grade, we bumped up from a 64 to a 7. That's a stiffer asphalt to give you more rut resistance. You get to the real heavy traffic situations like on a 9.5D and a 12.5D, we bump up to a PG76 grade, which is a very stiff asphalt. It provides a lot of rut resistance. Then on the intermediate mixes, on the B level, we stay with the PG64. On the C level, we use the PG64, but on the D level, we bump up to a PG7. Now on the base mixes, we stay with the PG64 all the way down, regardless of the traffic flow. And the question always comes up, well, if you're on your surface, on the C mix, you bumped up to a PG70, on the intermediate C mix, you stay with 64. And on the D level surface, you bumped up to a PG76, and on the D level intermediate, you only bumped up to a PG7. Now, why didn't we bump up the intermediate, just like the various traffic levels, just like we did the surface? Two or three different reasons. One of them is that if you remember that loading diagram, those intermediate base course mixes are down lower in that structure, so the load is spread out and the stresses are not as great, so you don't need that stiffer asphalt. Another reason is they're down lower in the paper structure, they don't get as hot. They're not as susceptible to lift. Probably the major reason is cost. As I said earlier, PG64 is the highest it's ever been today. And the indications are it's going to get even higher. But as I say, it's expensive enough as it is. PG70 is a stiffer asphalt. As far as the manufacturing and making of the PG70 versus 64, probably not a lot of difference in cost, but on average it'll run $30 or $40 a ton more. It's primarily for handling, storage, and so on, transport on longer distances because it's just not as readily available. But on the PG76, that's a polymer modified asphalt. I'll take something on the order of the PG64 and add polymer to it. That makes it real stiff when it gets, even when it's real hot. And hot weather temperatures. Very high performance asphalt, very expensive, maybe 2 to 4 times as much as PG64. So that really pushes that price up. You have to consider that, and if you can justify the use of it, the cost of it, it is a very high performance asphalt. But otherwise, you wouldn't want to use it because there's no gain, as far as rutting resistance on low traffic roads, so you wouldn't want to use it. So those are our three basic types and background on how those mixed types are selected. I would one thing I think of, if you notice here this SF 9.5A, whereas the rest of them are just S 9.5s. The SF is a special version of the 9.5 series mix. I always like to think of it as forces the gradation to be on the fine side as compared to what the standard gradation on 9.5 mix would be. Anybody ever heard of I2? The SF 9.5A is an old I2 design based using superpave criteria. It's a relatively fine mix that can be placed in a 1-inch thickness.
What is the 4.75?
The 4.75 is the old sand asphalt that I used to use. The old F1 mix.
F1. And the 12 is the I1 mix, called I1 mix.
The 12.5 is under superpave is really, it's a coarser mix than the old I1. you have to have a little bit of 67 stone in the road. The old I-1, it had a lot of, it had 78 stone in it, and it had a lot of 78 stone. And the intermediate mix is what we now call intermediate, or the old binder mix.
Right.
Any questions at this point? Two or three other things in this chapter I want to point out to you real quick. On page 3-4, you'll see a table there at the top, right? In fact, a couple of tables. Please note the heading of this particular section. These are guidelines for paper design purposes. Some people leave here thinking that these are the Bible, so to speak, for construction purposes. I would say they are pretty good guidelines for construction, but they're not, you can place mixes thicker or thinner than these numbers indicate here under the right conditions and so on. These are just guidelines that they use when they're developing that typical section. Likewise, down at the bottom, or in similar fashion, one number you may be, or numbers that you may be interested in, this column right here. These are the rates in pounds per square yard for 1 inch of depth. Please note, for 1 inch of depth that are used to compute quantities in contract by NCDOT. And for example, here, it varies. The coarser the mix is, the higher the unit weight would be, because it has more aggregate on a percentage basis and less asphalt than the surface. So that's why it's different. But these again are the numbers that are actually used to compute quantities in contract. Any questions? Another table you may be interested in is one over on page 3-6. These are the strength coefficients, and you don't have to remember all this, just know what it means. I'm not totally familiar with it myself. I just want to point out to you that when they're designing paper, they use different strength coefficients for different materials. Remember we said that the surface mixes had to need to be the strongest per inch of depth, and they assign a coefficient of 0.44 to surface level, with the exception of 4.75. We also in North Carolina use a 0.44 for intermediate mixes. Some states will use a slightly lower number. And then when you get down to asphalt base mixes, that rather than 0.44, that number is 0.30. Again, these are just relative numbers. So what that's saying is 0.30 is about 2/3 of 0.44. What that's saying is that on a per inch basis, intermediate mix is about 2/3 as strong as, base mix is about 2/3 as strong as intermediate for surface. Let's look at aggregate base. That's 0.14. 0.14 is about half of 0.30 for asphalt base. So what that's saying is that on a per inch basis, aggregate is about half as strong as asphalt. If you look at it in reverse, asphalt base is about twice as strong as aggregate base per inch of depth. And then when you treat it with that aggregate with lime, it becomes 0.13. If you treat that ABC with cement, it bumps it up from 0.14 to 0.23 and so on. But again, I just point these out to you to emphasize the fact that when we build a paper, we need to build it based on the typical that's shown. That's how they developed this typical. To carry the anticipated traffic, they incorporated these numbers. So build it like it shows on the typical section. And on typical sections themselves, there's one on page 3-7. Just quickly point out how you read these. As you get involved in the construction, you'll become more familiar with them. This is a very simplified typical section. The part we're interested in is the payments section itself. And on that typical, they'll have all kinds of dimensions, width, thicknesses, and this kind of stuff. And they'll show the various layers, and they'll designate them by some means, which will refer you over to the payment schedule. And the payment schedule will tell you what that layer consists of. It'll always tell you a mixed height, an average rate, and an approximate depth. In this case, it's talking about proposed 3 inches of ACSC, that stands for asphalt concrete surface pour, a type S945C at an average rate of 168 pounds per square yard in each of 2 layers. Now, why does it say some approximate depth and some average rate?
Could run into problems on the job site.
It's primarily because different mixes are composed of aggregates from different quarries which have different specific gravities, and that causes the unit weight to vary slightly from mix to mix. And so 168 pounds may not always be exactly 1.5 inches because of those differences. And that's why it says an approximate rate and an average thickness. Now, in North Carolina DOT work, it's the average rate that controls it. But I would say that in most cases, there are a few exceptions, in most cases, that average rate will be so close to that, give you that average thickness, so close that you can't measure the difference. Again, there are a few quarries in which that varies. But in NCDOT work, it's the average rate that controls when you're out in the project. Any questions about what we're talking about? If not, we'll move on over into section 4. Section 4 is about asphalt mix design and job performance. Again, most of you probably will never be actually involved in the design of an asphalt mix. Some of you may eventually do that, because under the QMS program, the contractor is responsible for designing the mix. The mix would have to be done by design technicians who have been certified by the NCDOT, and that certification process is one. As Wayne mentioned this morning, involves attending a mixed design class. NC State does it once for us, lasts about a week, and then the person has to go to a day and a half or so class that's put on by DOT to familiarize you with specific NCDOT procedures. The mixes do have to be designed by a certified, NCDOT certified technician. The reason we think it's important for you to have some basic concept of the design process is because that technician designs the mix in the lab, and then when we start producing that mix in the field, we're trying to duplicate what he designed in the lab. We run basically the same test on the mix in the field as we run on the mix when it's being designed. And so we think it's helpful, for you to understand what goes into that process and why it's important to produce that mix like it was designed. When you start varying from that design, you may be changing the properties of that mix. I guess you could make it stronger, but on the other hand, you can certainly make it weaker, and such that it would not perform as it was intended. That's the reason that we try to expose you to a little bit in this class to mix design. The basic concept when you're designing a mix is to determine what aggregate sources you have available, what it's going to take as far as the different sizes that are, assuming that they meet the specification, what different sizes are going to be needed to combine together to give you a gradation for the particular mix type that you're looking at. And then once you have selected those aggregates and determined what the blend is going to be required to give you the gradation, Then the next objective is to determine the optimum asphalt content for that particular combination. And this is where you start looking at what's called the volumetrics, basically the air void content in the mix and associated properties. So that's the, the basic concept. And then once you determine that optimum asphalt content for that combination, and assuming everything else meets the specifications, then you determine what the job mix formula is going to be. Basically, the job mix formula that's issued is a summary of the design information at the optimum asphalt content. And we'll look at that on mix design and a job mix formula here in a few minutes, and show you how we arrive at that job mix formula and associated target value. We've got a video here we want to take a look at. This video was put together a number of years ago, I might say early on in the SuperPavt implementation process by the Federal Highway Administration, I believe. But it's a very good overall summary of the SuperPavt design process. In the video, they talk about how the asphalt grades are selected. They talk about the aggregate gradation. They'll show you what they call a 0.45 gradation chart. And when they're doing that, they'll talk about the restricted zone. And the restricted zone was a concept early on in SuperPavt. It was thought that it would help to address the rutting. Pretty soon people found out that that was not the case and the concept was not valid. But when you start talking about the restricted zone in this video, just ignore that. It no longer applies. It's been removed, totally removed from North Carolina specifications, and as best I understand, from most every other. One thing I would ask to do is when they start talking about the compactor that you use to compact the specification, the mixes, on the SuperPavt dry core compactor. That's one of the major differences in the SuperPavt design process and the old Marshall procedure that we used to use.
Stains and scratches.